Test, test. Hello, Venjan.
Hello, Dr. Kelly.
Oh, I hear you. Yeah, thank you. Hello, Anand. Hello, Sayed. Who else is here? Oh, hello, Haley. Hello, Amir.
Hello, Dr. Killian.
Yeah, nice hearing you. Amir, can you say something? I'm checking different sound systems.
Can you still hear me?
Here now. So trying system one, please speak something.
Yeah, so I'm still
Okay,
speaking.
I hear, but it's very not loud.
Okay.
Trying system two, please say something.
Yeah, so can you hear me now?
Oh, so much better. Right, Ola?
Oh, good.
Okay. So we have a very special in-person attendee. So Ola is getting super extra credit for being the only one in class. Hello, Sayed. Thank you for switching on the camera. I really enjoy chatting in the way. I don't know where the camera is. Oh, here. So when you were doing votes, I think it was about 9 people who. Oh, hello, Amir. Thank you for enabling camera as well. Yeah, there were 9 people who told that they prefer Monday, but now we see only a little less. I know that. Oh, thank you, Haley, for enabling camera. I really appreciate it because by looking at your faces, I see feedback if I'm telling something reasonable or hello and thank you, Venjan, for you can just stay not saying anything, but I can see a question mark in your eyes if I'm saying something questionable. Okay. Focus on. Vola tells this room is not bad, but I think we can check and maybe find more comfortable room. Or if everyone will connect only from online, then it is not as important. Okay, so we have QVB 106 for today, and I think for tomorrow they gave us QVB 114 in the same building. So here are your votes. So we are continuing the lecture materials for this class. Again, most important meetings are on Wednesday, but the lectures that we agreed to have on Monday and Tuesday will provide you with the language and equations that you can copy paste into your reports and use towards your papers, publications, and degrees. Touchable. Okay, so my goal is to arrive to this equation by the end of the meeting. For the class, and my personal goal would be to learn how to. Oh, I already. It's good. It's good. Probably this room is not bad. So one can write on the board, and it will be recorded into PowerPoint. So we need to arrive to this slide, and again, this is not a theoretical course. So, by the way, do I share screen? Do I share screen, or it is on the camera? Please speak, because I do not see faces.
It's on the camera.
Oh, okay. It's not good. I need to share screen. Thank you, Haley, so that the quality of image will be better. Share screen. And now I go to presentation mode. Okay, better. And I think it's maybe a smart camera that tries to motion sensor focus on whoever is moves, but it is not as. So I need to get used to it. Okay, so I do want to arrive to this slide. And I know that 2 attendees of this class are also attending the morning class on the survey physical chemistry. So probably you are in the most lucky position, because you see some connections. So this there is a overlap of materials. So the goal for today's class is to arrive to this 2 underlined equations at the bottom. So what they are? It is time-independent Schrodinger equations for electronic wave function and for nuclear wave function. So we need to agree why and in which circumstances electronic and nuclear parts can be considered separately. And we need to consider them separately, because it's not possible to do simultaneously. It's too expensive. The approach that we are doing today is referred to as Born-Oppenheimer approximation, and we will practice this approximation until the maybe last 3 meetings in the class. The situations when one violates this approximation are really cool. It is important for non-adiabatic dynamics. It is important for combustions, explosion, and any vivid processes in extreme conditions. But if we characterize properties of materials in like low temperature or ambient conditions, then it is very typical to use this so-called Born-Oppenheimer approximation. I know that you can get bored or irritated looking on too many equations, but let me just bring a context who we are and what we are doing. So I probably will show slides with a little review, but briefly, we are bringing the background of quantum theory to molecular systems. So we are speaking about Schrodinger equation for molecules that have electronic and nuclear degrees of freedom, right? We do need this approach because we want to characterize materials, to find their properties, either optical, electronical, mechanical. So it's a task of this course. And electrons and often interatomic distances exhibit quantum properties. So we need to deal with these equations on one hand. On another hand, molecular Hamiltonian, when everything is taken into account, is not solvable. So we need to divide and conquer. So the two equations that we, what else? Thank you for submitting homeworks. When you are doing the homework, you are counting terms in the Hamiltonian, counting terms contributing to total energy of a molecule. And you are counting how many kinetic energies, how many potential energies for ion-ion interaction, how many electron to electron, how many electron to ion. So there are total five types of terms in the Hamiltonian, and the abbreviations are like T sub n, T sub e, V and n, VEN, VEE, right? When they all are together, it's just no way, not solvable. But if we are able to separate these terms and separately consider electronic and nuclear parts, we will be on a right way to do practical computations. And these equations can be programmed into the computers to solve our problems. So the equation on the left, so electronic part, this equation gives us set of electronic states, which here I refer to as phi sub a depending on r, so r lowercase position of electron, and it should be all electrons. I'm just lazy to write r1, r2, r3 and put vectors, but it's all electrons. And a is the index of eigenstate. So for quantum problems, for eigenvalue problem, the one equation has multiple answers, right? Like multiple orbitals. So A is an index. A can be like 1, 2, 3, 4, and for each of for different indices, there will be different solutions. The E sub A here, maybe I can use different color. No, I cannot. By some reason, it gives me only red. So E sub A is energy. It's also same index A. And A also equals, can be 1, 2, 3. So it's energies of eigenstates. And eigenstate phi sub 1 and energy E sub 1 are connected to each other. Like for one wave function, you have certain energy. This equation is still not ideal, but it is much easier than overall molecular Schrodinger equation. And here we include only 3 terms of the Hamiltonian, 3 terms of total energy. And there is kinetic energy of electrons, potential energy of repulsion between electrons, V sub EE, and then attraction between electrons and nuclei, V sub EN. This equation is allowed to practice because nuclei move so much slower than electrons. So on a time scale of any electron dynamics, one can assume that nuclei are just nailed down to the space and they do not move. It's ideally, it's not correct, but it is a good approximation. So if we assume that nuclei do not move, we can solve electronic problem. Okay. What is important in this equation? It is important that the values of eigenenergies will be slightly different if we redo this problem at different interatomic positions. Therefore, instead of simply E sub A, I am writing E sub A as function of R capital. So R capital symbolizes positions of ions or nuclei. And right now, I'm just doing overview without derivations. As time allows, we go through slides and I will try to show derivations. Now, this information, energy of electrons for certain interatomic distances can be used. I'm going to draw a line over the screen. So this one, and I'm going to the other side of the screen. Going here. So in some sense, this energy E sub A as a parametrically depending on R capital includes all the three terms: energy of kinetic energy of electrons, potential energy, electron repulsion, and electron nuclear interaction. So three terms. If we combine them with two other terms, kinetic energy of nucleus and nuclear attraction, it will be, in some sense, back the complete molecular Schrodinger equation. But here, we do not speak about electronic wave functions. We do not use these three terms as quantum operators. We use them just as a function. And these brackets act on the unknown function, which we symbolize with Greek letter chi, that looks like English and Latin chi. Maybe this room is not so perfect. Probably everyone was writing on this side of the board. It's all used chi sub b. So this is also wave function of ions. So it symbolizes that there is a probability for ions for each interatomic distance to be a little longer or a little bit shorter. And the Schrodinger equation to find this function chi sub b, and here I also need to add index w sub b. It's also an eigenvalue problem. So we find chi of r sub b, where b also goes like 1, 2, 3, and the value of this w sub b goes like 1, 2, 3, because it is eigenvalue problem. So by solving this equation, we import eigenvalue of electronic system as a parametric function. It's not an operator anymore, it's just a function. Function, not operator. And after we solve these two equations, we can find our overall molecular wave function as a product of electronic wave function chi and nuclear electronic wave function phi and nuclear wave function chi. So if you were not trying to catch me lying, if you were not trying to catch me wrong, you may believe everything I told. I was not intentionally lying, but this is an approximation. Something was skipped, something was missed as we went from full molecular Schrodinger equation to this pair of equations for the separation of variables. And the goal of today's meeting is to find what was missed and at which circumstances it is allowed. basically, since it is a last slide, I'm showing here there will be term symbolized by symbol theta sub AB, and my goal is explain what is this theta and why it is neglected. Okay, let me temporarily stop sharing and let's discuss a little bit. So we do have. Oh, I see London in the big room. Haley, you can say hi to London. Okay, so let's briefly check with everyone who is here. So, Haley, do you have any objections or questions about this little overview of today's material, or do you like approve it as a plan, or you want some corrections or focus on any specific part? Okay, good. Okay, Amir, is anything that you feel comfortable or discomfortable, like just please share your
Yeah, so there was something that I just didn't understand, and that was the eigenvalues you were talking about. I'm not sure what is that where is that coming from? Like, I know that there should be a matrix that you calculate these eigenvalues from, but I don't know what exactly it is. Where is it coming from?
Okay, yeah, thank you. I'm going to address it. So, Amir, eigenvalue. Yeah, maybe I'll address the question of Amir and then go questioning others. And even if you get delayed in other material, I think it's better if we all stay on the same page. So there will be, we do not lose each other in this material. So I'm going to insert new blank slide, go to presentation mode, and in Zoom start share screen. Okay, so what are eigenvalues? So I'm going to make a little interview, not in details, but just asking, is this concept completely new for you, or you heard something about it and you just need more details? So since Lowell in the class, Lowell, are you more or less comfortable with eigenvalues? Okay. So Amir already told that you want me overview it a little bit. Sayed, are you comfortable with this concept of eigenvalues, or you want more on this? Just briefly tell you're acquainted, not acquainted. So you are aware you did solve some problems on eigenvalues in some courses, right?
Actually, I don't have much idea about eigenvalues, but as you're answering it, so I'm listening to you.
Okay, yeah, thank you. Haley, how happy are you with eigenvalues?
I'm okay.
So this is not new subject. You can teach the subject yourself.
No, but I understand it enough.
Okay. If I do not know how to explain some concepts, I will ask you to help.
Maybe Lola instead.
I'll ask you both.
Did she say Lola?
Yes. Anand, are you? Do you have experience with eigenvalues?
I don't have any past experience. I am completely new to this subject.
Okay,
So,
that's fine.
yeah.
That's fine. Wenjan, did you have experience with eigenvalues?
Yeah, I have used the eigenvalue to calculate shift descriptor, kappa square, the molecular shift descriptor. But it's a tool. I just need to use it. I didn't know the exactly meaning, the concrete meaning.
Okay, yeah, thank you. So there are two styles of formulating eigenvalue problem. One style goes into the subject of linear algebra. And another style goes into differential equations. Yeah, it's very mysterious writing, so just guess what I wrote. So in the linear, I'll briefly summarize both so that we get understanding better, because it is different view on the same properties of mathematical objects and natural sciences. So simplest matrix is 2 by 2, right? And if we have an arbitrary matrix like A, B, C, D, right? We can formulate a problem that suppose we know, so all these four numbers are known. And then we have unknown vector with two-dimensional vector. It's like arrow in two-dimensional space, and they are not known. And now we formulate a problem so that for given matrix, for provided matrix, we act on unknown vector and obtain this vector again times some proportionality constant. So we are not in mathematical course. I'm not a mathematician. I'm not going to prove theorems, but each matrix has its personal eigenvalues. So if we know this, what? So I do not need the pen. I can write with a finger. No, I cannot. So for certain matrix, it will have only few vectors in overall space that will fit this equation. And if I would prepare it ahead of time, I probably would give examples. But in the whole, if you do matrix only 2 by 2, then in the whole two-dimensional space, there will be only two vectors that will fit this equation. But the most interesting thing that this is one equation, right? It's matrix equation, but it's one equation. But for one equation, there will be two solutions. One interesting thing. Another thing that if we change the matrix, the result of these vectors will be different. So the vectors which we get as a solution of such equations are characteristic of a matrix. So matrix has an ownership of the vectors. So matrix tells those are mine vectors, right? Therefore, it's ownership problem. So for each matrix, we can find its own vectors. And in German, eigen means own. Okay. Wenjan, make sense?
Yeah.
Okay, yeah. Amir, does it make sense by now?
Yeah.
Okay, thank you. Now, if you go to the subject of differential equations, we can make a combination of some differential operators like d, if it is one-dimensional, d. What is going on? Maybe I have some metal buttons that give screening. So like d dx plus d squared dx squared plus something else. There will be some coefficients here. So combination of derivatives is considered as differential operator, right? And this differential operator acts on a function that depends on x. So for each good operator, there is a set. Let's use the same index, A. One can find such function that by acting on this operator, like combination of derivatives, acting on a function, one will get the same function times proportionality coefficient, alpha sub A. The best example is exponential function. If you apply derivative to exponential, you will obtain exponential itself, right? So d dx e x equals 1 times e x. And instead of this problem, we can tell, no, I didn't knew what was this e sub x. It could be an unknown function phi. And this could be unknown number alpha. And then we have a problem. Find such function for which derivative will be equal to the function itself. So this is eigenvalue problem or eigenfunction problem. For single derivative, it's quite simple. But if you have anything more updated, then it is the whole subject of differential equations to find solutions. So for each operator, there is a set of personal own functions. So each operator claims like these functions are mine. And those are eigenfunctions. So there's eigenvalue problem. The eigenfunction and eigenvalue. Amir, does it make sense?
Sort of.
A little better?
Yeah, it's much better now, but I just didn't understand the constants in differential equations. Like,
well,
linear algebra.
right now we just need through practical applications, but if you plan your plan of study, you may just elect to take differential equations. If you do engineering and natural sciences, it's useful. One can survive without it, but with it, it's much easier.
Sure.
Okay. Let me check others. Anand, is it better? Can we go forward?
Yeah, now it is better.
Okay. Yeah. Thank you. Thank you. Sayed, is it okay to go further?
Yeah.
Okay. Yeah. Thank you. Haley, did you found any errors? Did you want to correct me?
No, I'm good.
Okay. Feel free to correct. Extra credit for if you find any errors. Okay. I think I asked everyone, right? Oh, you approve going forward, right? Okay. So right now it is a little too early to sign up for presentations, but it's just for your information in whatever 2 weeks. We will use one of the days for presentations, and we will need to make sign up between all attendees, either who is registered or auditing. We need to have presentations. Otherwise, it should be fair game, give and take. Okay? Thank you. And you see what last time we did only first 2, but I will speed up, and we have about 2 meetings to cover these things. After we meet on Wednesday, I will assign a homework. Here is a homework from last year, but it's already obsolete. Some people who were successfully doing this homework already got a paper out of it. So I'll design something reasonable based on skills how to draw molecules. So here, just a very quick recall. So we use theory, which is different stories about Schrodinger equation, eigenvalue problem, which is responsible for software that runs on the hardware to compute observables of materials and compare to experiment. It's just a summary of quantum theory that I'm happy to tell anytime, but I want to avoid because I'm telling it again and again very frequently. But basically, it is what we discussed today. Like eigenvalue problem, right? Gives many functions and many eigenvalues, right? And this is time independent. If it is time dependent, one just adds oscillating factor with imaginary unit. So then we considered a model of molecular hydrogen, found that there are 5 types of terms, and we did combine together everything that is related to electrons into separate part. Now we are finding eigenvalues of this electronic part, and I believe today we used the symbol phi, which will be slightly different for different positions of ions. Therefore, here these eigenenergies depend on positions of ions. If you find all of these phi sub I functions, they serve as a basis. It means any function can be represented as a superposition of basis functions. This is a general theorem from differential equations, and some of you who are already running Gaussian already heard and practiced this word, basis, right? One selects some basis functions to represent any orbital. Okay. Then, after the basis is known, we are taking this phi sub A basis functions and add them together to find solution of overall molecular Schrodinger equation. But the general question, by applying this trick of adding together basis functions, what are the factors in front of this each function? So we need just some coefficients, as is a very typical business in differential equations. But we know that our basis, electronic basis functions do depend on interatomic positions, not in a sense of operators, but as parameters. Therefore, this expansion coefficients also depend on these parameters on one hand. On another hand, if we take this expansion and plug it into full molecular Schrodinger equation, yeah, here is just a little better typing, we can use it as a tool to find this chi sub A. So we take this psi, plug it into here, and solve it. And as a result, we expect to get this chi sub a, which we didn't knew by now. So this phi sub a is already known, and chi sub a are not yet known. So there is a long way how to do it, and what I'm going to do, and I think we still can finish it. At least we can try to finish it in the remaining 30 minutes. So the actual lecture will be starts about now. Hello, Hanman. I'm happy to see you connected. We actually start the lecture right now. Before it was just overview. So here is our molecular Schrodinger equation. Kinetic. Wait, just a second. Kinetic energy of nuclei, potential energy of nuclear attraction, everything that relates to electrons. And here I want to put big bracket and apply it to the overall wave function, which we represent as a product of chi times phi. Chi is known, phi is known, and chi will be found. So, and here it equals to eigen value, which multiplied by this summation chi times phi. So there are no tricks up to now. Nothing has been neglected. I just, it is, this stage is yet exact. So we're just looking for a solution in a specific form, and we are plugging the specific form into molecular Schrodinger equation. At this point, phi is known, chi is not known. And we hope that phi can be removed, neglected, and then there will be equation for chi that we will solve, and we will be happy. So it's just the same thing what we do. So this expansion over basis functions is plugged into molecular Schrodinger equation. And just a reminder, this red H includes 3 terms. So as we go through slides, this equation is not very long, but longer than usual. Therefore, and I want to put special care about each term. Therefore, I'm chopping this equation onto 4 lines, just to have full control of what is going on. Right now, again, it's repetition of what was before. So each term, and after each term, there is an expansion, chi times phi, right? So they are the same. So my goal is to remove phi sub a. And there is a trick which we briefly reviewed on the morning class on advanced PChem. So Lola was teaching all of us of orthogonality property, right? So there is a so-called orthogonality property which is designed intentionally to solve all our problems, to remove functions from such equations. Even if we get delayed and postpone some materials for next time, I think there is a time for a little interview because I want to check if everyone feels happy about the concept of orthogonality. So I stop sharing. I will add another empty slide just in case if comments will be needed. Okay, and let me double check with everyone. Amir, did you hear about orthogonality of functions before? Do you feel comfortable or not quite?
Actually, if you explain it, I would be able to say if I've heard it before or not.
Okay, yeah, that's fine. Anand, did you hear about concept of function? Okay. Venjan, do you have experience of orthogonality of functions?
No.
Okay, that's okay. Sayed?
No, it's new for me.
Okay, good. Hanmand?
For me also it's new.
Okay, and if it is comfortable for you, please enable camera. Then by visual contact, I can see if you accept or reject some ideas. Yeah, thank you. Who else? I think I've asked everyone. Okay, so by majority of votes, I'm returning back to slide presentation and just will give some brief comments on the orthogonality. So go na and one always can try looking into Wikipedia and it will they have answers on math and natural science. There are unambiguous answers, so that one can trust. So let's appeal to two concepts again. Linear algebra and differential equations. In linear algebra, we can solve eigenvalue problems. We can get different vectors. And vector, let's say, C sub 1 is x1, y1. Vector C2, x2, y2. And visually, vectors can be represented as arrows in the space x, y. Suppose here we have vector C1, little arrow here, and then it is represented by projections x1 and y1. Does anyone approve this little formulation? If you do not like it, just raise your voice. Everyone approves. Now, we can draw the second vector, which I will probably do it wavy so it differs. So it will be C2. And then it has projection of x2 and y2. So these two-dimensional vectors should make everyone happy because we all did a little bit of vectors in high school, right? So vectors can be parallel, can be perpendicular, and can be at some angle, right? So if two vectors are parallel, like C1 is parallel to C2, then one uses words like parallel or collinear because they go along the same line. And mathematically, it means that x1 equals x2, y1 equals y2 with proportionality coefficients. And proportionality coefficient is the same for both projections. Like one vector can be longer than another, but they are oriented in the same way. Make sense? Now, if the vectors are orthogonal, C1 perpendicular to C2, we always, in this two-dimensional case, we can just draw. They have 90 degrees between them, right? But there is a mathematical way to assess it. So one may define a procedure of dot product. Haley, are you happy with dot product? Dot product. Say yes, you should be happy. Let me check with everyone. Amir, are you happy with dot product? Good. Anand, are you happy with dot product? No, okay. Venjan, are you happy with dot product? Okay, thank you. Sayed, are you happy with dot product? Okay. Hanmant?
Yes.
Okay. Yeah, I'll briefly cover and then we'll go forward. So here is our definition of vectors, and we can define dot products of C1 times C2. I'll write it down. Here is a little better space. C1 times C2 as length of vector 1 times length of vector 2 times cosine between them. And we can use like angle beta. So what is cosine of 0? Anyone is welcome to speak out loud.
One.
Cosine of 0
One.
is 1, correct. So if two vectors have angle equals 0, it means they're parallel, and it means cosine will be equal 1. So it's same as like no cosine. If the vectors are perpendicular, angle is 90 degrees. What is cosine of 90 degrees?
0.
0. So for 90 degrees, it will be 0. So depending on whether they are parallel or orthogonal, dot product will be either 0 or 1. Right? So by using concept of dot products, we can separate parallel vectors and perpendicular vectors. So this concept works well for 2 dimensions, but it can be really well done for any amount of dimensions. So let me give another equation for dot product. So it is x1 times x2 plus y1 times y2. So it is a product of projections, summation of products of projections. And absolutely the same concept can be applied to 3, 4, 5, 10, 100 million dimensions. So vectors in any amount of dimensions. So I'm covered the linear algebra, and now let's use the same concept for differential equations. I will stop sharing for a second. I know that we are about over time, but I'll finish to some logical point. Does anyone need to depart sharply at 5? No? Okay, thank you. So screen. Okay, for differential equations, one can use, let's say, function 1 of x and function 2 of x. Now, for these two functions, one can define an analog of dot product. What if one takes phi 1 of x times phi 2 of x and integrate it over the whole dx space? If we do this operation numerically, it will be phi 1 in point x1 times phi 2 at point x1 plus phi 1 at point x2 times phi 2 at point x2. So this one is analog of our x1, x2. This is our analog of y1, y2. So values of functions at different points of space, and here we need multiply by dx. Multiplication of values of functions at different value of argument are equivalent to projections of linear algebra thing, plus so forth. So if this integral of multiplication of two functions finally gets to 1, we call that these functions are parallel. The word parallel is too geometrical, and one tells function is, then the function is itself. Or if it is non-zero, just some number, one can say that they are collinear, they are proportional, but it's a question of semantics. And if this product of function equals 0, we can say that functions are perpendicular. And perpendicular, again, is like kind of 2 or 3-dimensional. Instead, one tells that they are orthogonal. Orthogonal. So if you have two functions, we can do a mathematical procedure which has the same meaning as dot product and tell whether these two functions are parallel or perpendicular, equal to each other or orthogonal. And this procedure can be set up into computer, and it can be done again and again for any function. Let me check if everyone is happy with this little formulation. Amir, make sense? Okay, Haley, do you approve? Thank you. Anand, is it better now? Okay, thank you. Venjan?
Yeah, it's good.
Yeah, thank you. Hanmant?
Yes.
Okay, thank you. Sayed?
Yeah, it's fine.
Okay, thank you much. If you guys decide that it's time to stop, I can, but if you have a few minutes more, I better go through a couple of slides. What do you think?
Yeah, it's fine.
Okay, yeah, then I'll go through a couple of slides so that we like invest into our future. So the orthogonality property, let's look on it once again. By performing this integration, we are getting either 0 or 1. So before we start operation, we had two functions. After this operation, we have just a number. So if we want to delete function somewhere, one function, we need to multiply it by another function and integrate. So orthogonality property helps us to erase a function in the mathematically rigorous way. Okay. And there is a symbol which is called Kronecker delta. Like if we have arbitrary functions a and b, we can tell that multiplication of two functions will be delta AB, which is either zero or one. 0 or 1, depending on whether indices coincide or are different. In our equation, main equation that we are trying to solve, we do have phi sub a, and we do not have integral. But I suggest to complement it towards this orthogonality thing by multiplying each term by integral and phi sub b from the same set of functions, from the same basis set. So the green writings correspond to what we had before. The red writings are the same for each of the 4 lines. So it is integral dr phi sub b, integral over di, dr phi sub b, integral over dr phi sub b, integral over dr phi sub b. So we are going to use the same the following idea. This phi functions depend only on positions of electrons. The chi functions that we need to find depend only on positions of ions, uppercase R. So there is a hope that we can perform this integration, and this integration will eventually remove phi A and phi B here and there, phi A and phi B here, phi A and phi B here, phi A and phi B here. And as a result, we will get an equation for chi, for nuclear wave function only. Okay. Let me check if one can either stop here or go. Well, probably we need to start from this point when we meet tomorrow. I suggest we make a stop here, but if you really want, I can go there. Like, let's vote. Is it okay to continue tomorrow? Okay, let me ask. Who is speaking?
Maybe intermediate. For me, it's better to continue tomorrow. But the media bottle, like,
Oh, okay. Amir, is it okay to stop, or you strongly want to continue?
No, we can continue tomorrow.
Ah, tomorrow, okay. Haley, is it okay to continue tomorrow? Okay. Anand, is it okay to continue tomorrow?
Yeah, it is okay, but if you have time, then we can continue.
Okay. It's possible, but let's probably better you think about what we talked through the night, and then when we will be fresh, we'll continue. I do not want you guys to overwork and keep energy for your other activities. Wenjan, is it okay to continue tomorrow? Okay. Hanmant, do you approve? Okay, thank you very much. I really like the subject, and I would be happy, but it is wiser because there were additional pieces of information that were like I originally didn't plan them, but they really needed so that we stay on the same page. So we used about the same time as amount of time as planned. So let me suggest we finish now, continue tomorrow. Thank you for investing your time. everyone is welcome to disconnect and depart the room.
Yeah, at least I can show her the
Thank you.
last two steps. The
Yeah,
fourth
thank
step
you.
is kind of.
Okay, okay.
Also,
So
like,
meeting is done, and if there are any questions,
I
I will stay connected and answer them. But if there are no questions, you are welcome to disconnect.
Okay, yeah, she has to see that first.